Hi there. Well, thanks for joining us. This session is to give you just a little bit more of a working familiarity with the mole map. So we've just kind of quickly introduced it, but I'd like to give a little tutorial here that you can refer to online that explains a little more, step by step how you can use the mole map. And you're welcome to use this on the upcoming assignments. So I think it's really going to be helpful to you. So let's just dig right in. Let's look at a problem. So what I've done is I've just kind of shrunk the mole map down over here in the lower left-hand corner, and let's take a look at an actual problem. And in the course of working the problem, we'll kind of demonstrate how the mole map is used. Okay, let me adjust my screen here a little bit. Okay, this problem. How many carbon atoms are contained in 75 grams of carbon? So what I'd like you to do is try to work this problem if you can, see how far you can get, and then and then you can restart the video, and I'll kind of demonstrate how you can work this. Okay, so what you're given in the problem is that you've got 75 grams of carbon. So on the mole map, if you think of this as one analogy I've made with some of my classes is it's like a subway map. So for this particular problem, we're starting right here. We're at the mass station, and we need to take the subway to the mole station, which is kind of like Grand Central, and then from there we need to go to particles, because the problem is asking how many carbon atoms, and so carbon atoms are clearly, that's a particle problem. So step one is we need to get from mass to moles, and then step two is get from moles to particles. Okay? So the way I start these problems, as I've said in class, is I start by writing down what we're after. So the number of carbon atoms equals, okay, and then I put down what we're given. So 75 grams of carbon. And now the first thing we need to do is we need to convert the mass to moles. And since we're going this way, left to right, we're going to need to take this train, so to speak. So we need to convert the mass of carbon to moles first. And to do that, we're going to use 1 mole over the molar mass of carbon. So that's 1 mole over. You know how to use your periodic table, so you look up since this is just a pure element, you can just grab the atomic weight from the periodic table, which is 12.01, and that's grams. Okay, and so now when you divide the 75 grams by the molar mass of carbon, that's going to give you the number of moles, because I think you can see that when you do your unit analysis here, you're going to end up with moles. But we are only halfway through our journey on the way to the particle station. So once we have moles, then we need to apply a second conversion factor. We need to multiply by Avogadro's number. Okay, so let's do that. Because we know that there's 6.02 times 10 to the 23rd atoms, excuse my writing, in 1 mole. Okay? And now, when we do our unit analysis, you can see that now moles cancels with moles, and we're going to end up with atoms. All right? So now, so that's how we traverse. So conceptually, that's what we're doing. We're trying to get from this, from a certain amount of carbon in grams, and we're trying to convert that to the number of carbon atoms. And in order to get there, we have to apply 2 conversion factors. First, we have to multiply mass by 1 mole over the molar mass of carbon. That gives us moles. Then we need to multiply by Avogadro's number over 1 mole, and that gives us the number of particles, which in this case is atoms. Okay, so let's do that. So I take 75, divide by 12.01. Okay, that gives me 6.24 moles. And now I multiply that by 6.02 times 10 to the 23rd. And I get, when I do this out, I get 3.8 times 10 to the 24. My calculator actually says 3.759367 and so on, but we are given two significant figures in the problem, so we really should only keep two here. So that's that many carbon atoms. All right, and that's our answer for that one. Okay, so let's try the next one. Let's see here. Actually, I think I may have. Yeah, I'm skip the first one actually, but that's perfectly fine. All right, now in this one, again, this is to just illustrate the using the map. This time we're being given a certain number of carbon atoms, and we're being asked, okay, how many grams would you need to have that many atoms? So now I think you can see that we're starting with particles. So we're starting on that part of the mole map, and we have to get from there to moles, and then from moles to mass. So we're going to be applying, well, let's see, what's the first conversion factor we need to apply? This one. We're going to have to divide by Avogadro's number, and then we're going to need to multiply by the molar mass. Okay, so let's set that up. How many grams? Okay, so mass of carbon equals 7.3 times 10 to the 23rd atoms. All right, so I've got things started out. Now remember, even if you completely freeze up and you don't remember how to do anything, you can at least put down this much, right? You can start by stating what it is you're trying to find. That's what the problem's asking for, and then equal sign, and then put down what you're given in the problem. Then it's just a matter of applying the correct conversion factors. So the first one is 1 mole, and now you're going to divide by Avogadro's number. And then that gives us the moles, and then we need to multiply by the molar mass. Again, we're talking about carbon. Carbon is 12.01 grams over 1 mole. Okay, and whoops, I just threw my calculator on the floor. Now, what we do is we start by taking 7.3 times 10 to the 23rd. We divide that by 6.02 times 10 to the 23rd, and that gives me 1.21 moles. And then I multiply that by 12.01, and I get, I'll change colors here, I get 14.656, and so on. But technically I really should only keep two simple figures, so we're just going to round that to 15, and that's grams of carbon. Okay, so there we go. So that's how you can use the mole map to solve these mass to particle and particle to mass problems. Now, one last problem, just for a bonus. Okay, so what if you're faced with this kind of a problem? Now, I would like you to try to tackle this problem and see how far you can get. So push pause, give it a shot, and then when you get as far as you can, or if you get all the way to an answer, then restart the video, and I'll show you how I did it. Okay, so I'm going to do this in 2 slides. The first slide, we are going to need to, we're going to need to calculate the molar mass of copper 2 phosphate. That's a given, because on the next slide, let me just put the map up here. I think you can see that we're being given a certain number of formula units. Okay, so copper 2 phosphate is an ionic compound, And so the fundamental unit is the formula unit. And so we're going to be starting right here on the map. And it's asking us how many grams. So we're going to go from particles to moles, and then moles to mass. And to do that, we are definitely going to need the molar mass of this compound. So let's go back and let's get some practice at calculating a molar mass. All right, so first of all, this is where we need to draw on our expertise with chemical names. Copper-2 phosphate, so what we know is if it's copper-2, the copper has a 2+ charge. Phosphate, okay, hopefully you look this up on your polyatomic handout, and you can see that it's a 3-. And so when we put this together in a compound, if you want to do the crisscross method, that's going to be Cu3 and then open parentheses PO4 with a 2. So here's the chemical formula for copper-2 phosphate. Now our task is to calculate the molar mass. All right, so all I'm going to do is I'm just going to take an inventory of the various elements. So we've got copper, there we go, and we've got phosphorus, and then there's oxygen, right? So I don't see any other elements besides those three. If you look up the atomic weight of copper, that's 63.55. Phosphorus is 30.97. And oxygen is 16.00. Okay, now, okay, sorry, I had to pause there myself. My 2-year-old daughter just came down, down to the basement, so it might get a little loud here, but we'll do our best. Okay, so now we've written down the atomic weights of the 3 elements that we're dealing with, and then the next thing we got to do is we have to now carefully look at the number of each of those atoms in a formula unit of the compound. So there's 3 coppers, so we're going to have to take the atomic weight of a copper and multiply it by 3. And when we do that, we should get 190.65. All right. How many phosphorus atoms do we have? Well, don't forget the 2 is going to distribute through the parentheses. So there's 2 phosphorus atoms. So times 2. And when we do that, that's 61.94. And then we have how many oxygen atoms? 2 times 4, that's 8. All right, so we got 2 times 8, and that's 128.00. And then we have to add this all up. And when you do that, if I did my math correctly, that should be 380.59, and that's grams per mole. That's the unit on that. Okay. So, and I just want to point out that we got to remember that the the convention that we said we would agree to in this class is when we are using atomic weights to calculate molar masses, we're going to take those atomic weights and round them to hundredths place or 2 decimal places. Okay, just that way it'll kind of keep things consistent. All right, so if you're able to get something around 380.59, you're doing great. All right, so now we can use that molar mass over here on the next slide to try to convert this number of formula units to the mass in grams. All right. Now the first thing I'm looking at is when I see this number, 1 times 10 to the 20th, ask yourself, is that about a mole? Is that about an Avogadro's number? Or is it a lot more? Or is it a lot less? Well, if you compare this number to Avogadro's number, you'll realize that it's actually a lot smaller than Avogadro's number. Okay, so we're being given a lot less than a mole of copper-2 phosphate. We've got like 1,000, less than 1,000. So we're probably going to have we're probably going to have something under a gram when we get all done with this thing. Okay, so let's try to set this up. All right, let's see. First thing. Okay. Yep. Thanks, Julie. Julie's giving me some. Number one, set up the thing that we're trying to calculate. Okay, we're trying to get the number of grams. Okay, and then we put down what we've been given. So that's 1 times 10 to the 20th. Formula units. And we're here. Now we need to apply this conversion factor, don't we? We got to divide by Avogadro's number, so that's 1 mole over 6.02 times 10 to the 23rd. Okay, and so when we divide by Avogadro's number, that'll give us a number of moles, and then from there, now we need to make the trip over to mass. And for that, we're going to need to apply this top conversion factor. So this is where we need the molar mass, which was 380.59 grams. And that's over 1 mole. Okay, cool. So now we can do some units analysis. Oops, I should have put formula units down here because that's the particle, that fundamental unit that we're using. And so now when we cancel units, we can cancel formula units, we can cancel moles. You can see we're going to end up with grams. And you compare that with what we set out to calculate, and you can see that everything worked out. We must have set things up properly, so that's comforting. And so when we take this number and divide it by Avogadro's number, and then multiply by 380, let's see what we get. Okay, so I'm going to do this right along with you. 1 times 10 to the 20th divided by 6.02 times 10 to the 23rd times 380.59. Okay, and indeed, I'm getting something, quite a bit less than 1 gram, which is sort of what we expected. I'm getting 0.0632. Okay, so we've got 3 significant figures in the number we were given, so we can keep 3 significant figures here. And that's grams. And there we go. So if you made it all the way to that point, man, you're doing great. Okay, so thank you. Thanks for joining us, and we'll see you tomorrow.